Hello everyone, welcome to another live YouTube classes from Brilliant Qatar. Today we are going to discuss, revise a quick review of concepts from few chapters of 12th physics, and we'll do some questions also along with it. The chapters, as you see, EMWaves, dual nature of matter and radiation, atoms and nuclei, and semiconductor electronics. So these three chapters we'll go for a quick review of the concepts along with, as I told you, some questions. Okay, let's start. As far the chapters are concerned, the five chapters we are going to deal with. The first one, dual nature of matter and radiation. You can see the average expected weightage from this chapter for boards, right? Expected weightage, because like it is a part of dual nature of matter and radiation is 1 unit with 4 marks. Atoms and nuclei together is another unit. Together we have 8 marks, so we expect 4 marks each from atoms and nuclei. That is why I told you expected weightage. And semiconductor electronics is a single unit of 7 marks as per the weightage given. Whereas electromagnetic waves, we expect 2 marks from that. It is a part of that optics unit, right? So we expect 1 or 2 marks from electromagnetic waves also. Altogether, you can see 21 marks out of 70 from these 5 small chapters. It is approximately 30%, right? Exactly 30% actually. Okay, so the plan is to run through the concepts of these chapters, a quick review of the concepts with some questions, like very few number of questions we'll try to finish within time. Okay. When we come to dual nature of matter and radiation, it is a very small chapter. We have to discuss particle nature of radiation or wave, and also wave nature of particle, right? That is why the title dual nature of matter and radiation. You can see particle nature of radiation. We are going to explain photoelectric effect. The major topic that we have to cover in that region is photoelectric effect. Photoelectric effect can be explained only using particle nature of light, particle nature of radiation. Okay, so when we discuss particle nature of radiation, to explain that, we use photoelectric effect concept. So we have an experimental study of photoelectric effect and Einstein's explanation, right? Einstein explained that using Planck's quantum theory, we know, yes, and he introduced photon theory of light to explain photoelectric effect. I told you particle nature of light, correct? Okay, then we have some graphs, repeating questions from the graphical representation of factors affecting photoelectric emission. We'll come to that. Then the second part of the chapter is particle nature of wave. Wave nature of the particles. Particle behave like waves according to the Broglie hypothesis. So just fundamental concepts of that only we have to discuss from this part. So it's a very small chapter with 1 or 2 concepts. We'll run through the concepts quickly. Okay, when we come to photoelectric effect, we know photoelectric emission. Photoelectric emission is emission of electron from a metal surface when radiations of suitable frequency incident on it. Photoelectric, right? Energy is provided in the form of radiation, in the form of light, and because of that, when light incident on the metal surface, electrons are emitted. Photoelectric emission. So the terms that we use in this discussion, some important terms. One, we know photosensitive material. What do you mean by a photosensitive material? Any material, any metal which exhibit photoelectric effect is said to be photosensitive material, right? So if you want to carry out photoelectric emission, that material should be a photosensitive material. For example, zinc, sodium, right, nickel, so many examples we know. And photosensitive material is a material which exhibit photoelectric emission. Okay, then photoelectrons, another term we used in our discussion. Photoelectrons. Photoelectrons are electrons emitted from the metal surface when radiation incident on it, right? Due to photoelectric emission, electrons emitted from the metal surface are called photoelectrons. These photoelectrons constitute a current in the circuit which is called photoelectric current. And this photoelectric current is a very important terminology for us. It's a very important tool actually to study photoelectric emission, because when electrons are emitted from the metal surface, we cannot We cannot see electrons, right? Yeah. So we can identify or we can understand there is photoelectric emission happening only by checking photoelectric current in that experimental setup. When we come to that, we'll explain that also. Okay. So photoelectric current is the current constituted by electrons emitted from the metal surface, which are called photoelectrons. Okay, another important term was threshold frequency, right? We know threshold frequency. What was threshold frequency? Which is denoted by nu naught or F naught. Threshold frequency is the minimum frequency of incoming radiation. When light incident on the metal surface, photoelectric emission happens. So the incident radiation should have a minimum frequency to emit electrons from this metal surface. That frequency is called threshold frequency, and corresponding to that, energy equivalent of threshold frequency is called work function, right? Work function of a metal. So work function is denoted by phi naught or W naught. You know, that is usually that is how we usually represent work function of a given metal. So work function of a given metal is minimum energy of the incoming radiation, right? Minimum energy of the incoming radiation to emit electrons from the metal surface. So these are all some important terms that we have to remember, like when we start explaining photoelectric emission. We are coming to the detailed study of photoelectric effect. We will use all these terms in our discussion. Okay, right. Experimental study. That is one of the important topic from this chapter. We are going to understand, we are going to study what are the factors affecting photoelectric emission. And we get repeating questions from this part also, like factors affecting, we have to explain three factors: intensity of incident radiation, frequency of incident radiation, and applied potential. Three important factors. We represent them graphically: dependence of intensity, you know, on photoelectric emission, frequency, and also applied potential we represent graphically, and that graphs are very, very important. When we go through the past papers, you can see these graph questions are repeatedly coming. So what was the experimental study? We used a photosensitive material here. This is a photosensitive material. Usually we use zinc there. And zinc is sensitive to ultraviolet radiation. So we use a UV source and we connect zinc in an evacuated glass tube. Right. So if zinc is sensitive to ultraviolet radiation, when ultraviolet radiation hit the metal surface, we know electrons will be emitted. Photoelectric emission happens. And these electrons will cross the distance by themselves and they constitute a current in this circuit. We have an ammeter connected here to measure which current? Photoelectric current, the one which we mentioned before, right? Photoelectrons constitute a current in this circuit, and they are called, that current is called photoelectric current. And I told you that is an important tool to understand photoelectric emission. Otherwise, we cannot see, as I told you, we can't see that electrons going, right, emitted from the metal surface. If more electrons are emitted, that is understood from the current. More current will be flowing through the circuit. So if more current flows, that means more electrons are emitted. Less current, less electrons are emitted. That is how we are going to study that effect of these different factors. Okay, so this is the experimental setup. We are going to check what are the factors affecting and how it is affecting. The first one was intensity. Effect of intensity of incident radiation. Right? We used a ultraviolet radiation. I told you zinc is sensitive to ultraviolet radiation. So ultraviolet radiation we used with different intensity. Intensity means the brightness of the radiation, right? So we are going to start with a dim source of ultraviolet radiation. Slowly I am increasing the brightness. Intensity I am going to increase. Okay, and it is found that, as we know, intensity, when you increase the intensity, photoelectric current is also found increasing. The graph was a straight line, right? The first important graph we got from the first factor. Yes, intensity of radiation and photoelectric current, they are directly proportional. So intensity or photocurrent is directly proportional to intensity. Okay, see, I'll change the color. Photocurrent is directly proportional to intensity, and I told you photoelectric current is constituted by emitted electrons, correct? So if you get more current, that means more electrons are emitted. So if you have greater current, more number of electrons are emitted. So we can say number of electron emitted, number of photoelectrons emitted is proportional to what? Intensity. right, intensity of radiation. So if you use a bright source of ultraviolet radiation, what happens, you know, zinc yield more and more electrons. More electrons will be emitted from the zinc surface. That is the first observation we made from experiment, okay, experimental study. And when intensity was zero, see, for when intensity was zero photoelectric current. For any non-zero intensity, it is important. Any non-zero intensity, we get a current, right? Yes, that is why the graph starts from the origin. Yes, okay. Next factor was effect of frequency. More important graph than the previous one, right? Because we can see this one frequently in our question papers. Effect of frequency of radiation. This time, frequency of radiation. When we changed the frequency of radiation instead of intensity, see, before we changed only intensity of radiation, we kept all other factors constant. I didn't make any change in the circuit. Only intensity of the source was changing. Now, I kept even intensity a constant. I'm changing only frequency. Frequency, we are starting with low frequency ultraviolet radiation. So ultraviolet radiation has a frequency range, we know, right? Starting from the minimum, we are going to the maximum. Okay, and at that time, it is observed that photoelectric current is independent of what? Independent of frequency. When you change the frequency, right, when you change the frequency of incident radiation, you cannot see any change in the photoelectric current. That means number of electrons emitted cannot be changed by changing the frequency of radiation. What should we do for that? If you want to change intensity, number of electrons emitted, if you want to change, you should change the intensity, not the frequency, because frequency has no role in that. It is independent, you know, electric current is independent of frequency. But something else was found varying. What is that? Kinetic energy of photoelectrons. Emitted electrons. Electrons emitted from the metal surface from the experiment we have seen. Electrons are emitted from the metal surface. Their kinetic energy is found varying when we changed the frequency. Correct? And it is found that kinetic energy of photoelectrons directly proportional to the frequency. That is why the graph becomes a straight line, we know. And this point in the graph is very, very important. We have seen before intensity graph started from the origin, because for any non-zero intensity, see, photoelectric current is possible. At zero intensity, no current. Here, zero frequency, no kinetic energy. Not only for zero, for a range of frequency, no kinetic energy for like photoelectrons. No photoelectric emission happens, and the minimum frequency required we defined in the very beginning, right? There is a frequency limit. For any frequency, we cannot emit electrons from the metal surface. There is a minimum limit, which is called threshold frequency. So from that up to that, there is no photoelectric emission possible. From zero frequency up to nu naught, threshold frequency, no emission. After that, it is directly proportional. So kinetic energy of electrons, emitted electrons, is directly proportional to frequency. That was the second factor, right? Intensity and frequency. Fine. And the next one was applied potential, effect of applied potential. We applied potential in two different ways. They are called accelerating potential and retarding potential. What was accelerating potential? When we connect negative terminal of the cell. See, look at this. The terminals of the cell I will mark here. It is black, you can see. Yes, this is how the cell is connected. So negative terminal of the cell is connected to the photosensitive material, the zinc, inside the evacuated glass tube, and positive terminal is connected to the metal anode. See, because of that, there will be a negative potential from this end and a positive potential on the other, right? What happened to these electrons? Electrons get a push from behind and a pull from the other side. Electrons are accelerated. Electrons are accelerated. That is why this connection is called accelerating potential. When you provide potential like this, it is called accelerating potential, right? Yes. Then when you connect accelerating potential, the graphical representation, see, accelerating potential is taken along positive x-axis. You can see in the graph. This is retarding potential. We'll come to that later. Look at the graph. The graph starts not from zero. which means even the applied potential was zero. Even when the applied potential was zero, there is a non-zero current in the circuit, right? This is photoelectric current. Photoelectric current. Yes, it is given as I here. I is the current, which is photoelectric current. Yeah, you can see, even at zero applied voltage, there is a non-zero current. Graph is not starting from the origin. It is because some of the electrons, see, I told you the use of that accelerating potential is to push electrons from one side to the other so that they can complete the circuit. They can constitute a current in the circuit. But some electrons will have enough energy when they come out of the zinc surface. They will have enough energy to cross the distance by themselves without the help of the external potential. They have enough energy to cross this distance and complete the circuit. You know, they can flow, they can make a current. That current is the current which we can mark in this graph. This is the current at potential is zero potential, right? Okay, so that current, you know, this is the zero potential current. We applied zero potential. At that time there was a current. Then I started increasing the applied potential. Look at this. We have a rheostat here. This is a rheostat, right? Variable resistance arrangement. We can adjust the voltage, the applied potential V. You can adjust that potential. You know, that potential will start pushing the rest of the electrons. Not all the electrons, like, you know, some of them only moving in the beginning because of their own energy. The remaining electrons will be pushed from this side with the help of this accelerating potential. So definitely more electrons will join the flow. Initially only some of the electrons can constitute the current because only they had enough energy to cross the distance in the evacuated glass tube. Now the external potential will push the remaining electrons to increase the current, correct? Which means when you increase the accelerating potential, current is found to be increasing, right? Current is increasing. That's what the graph say. But it won't increase up to any value, up to infinity, no. There is a constant. The current, if all emitted electrons are accelerated to the other end of the electrode, then no more electrons are remaining in the, like, you know, on the, it's coming from the zinc surface. All emitted electrons are accelerating, which means current is going to be a maximum. If you want to increase the current beyond that, more electrons should be emitted. That is not possible by increasing the potential. If you want to emit more and more electrons, what should we do? We have to increase the intensity. That is what we have seen, right? Okay, so accelerating potential will help you to increase the potential, increase the photoelectric current up to a saturation current, up to a maximum value. Okay, yes, and this current is called the saturation current. So what did we actually do? When we apply some potential, only some of the electrons were moving from one end to the other because of their own energy. They had enough energy. The remaining electrons are not able to cross the distance. Coming out of the zinc, they don't have enough energy to cross the distance. Those electrons are helped, right? They get help from the external potential. So external accelerating potential will push them, and they are also joining the flow. Now the current is increasing. When all the electrons are accelerated, current becomes a constant. Okay, that is how the graph is varying. Graph is very, very important. I will show you some sample questions at the end, how we get questions from this part. Okay, now what happens when we reverse the potential? We connected zinc or that photosensitive material as negative to the negative terminal of the potential, right? And the other one to the positive terminal. Now we are going to flip the cell. If the photosensitive material is connected to the positive terminal of the cell, so the cell should be flipped. This will be positive, negative, right? This will be the connection. When we do this, this potential changes into positive, no? Negative changes to positive, positive changes to negative, which means it will give the opposite effect. Electrons which are trying to cross the distance are pulled back by the zinc, right? From this side, there will be a pull from the zinc plate and a push from the other electrode. Okay, so electrons are started decelerating. That is why it is called a retarding potential or decelerating potential. Okay, so the retarding potential, when you increase the retarding potential, what happens? At zero potential, I told you, some of the electrons were able to cross. For example, 3 electrons were having enough energy to cross the distance. Emitted electrons, 3 electrons. Actually, 5 of them were emitted, for example, but these 2 don't have enough energy to cross the distance. So only these 3 were crossing. Correct? Yes. So without the help of external potential, those 3 electrons will constitute a current. That current is this, non-zero current. Okay. Now when we reverse the potential, when we reverse the cell, it is a retarding potential. Even these electrons, those who were moving by themselves, are pulled back, right? Because of the potential. So when you increase the potential, electrons will be stopping one by one as per their energy. The last electron which is stopped will have the most energy. The weak electrons will stop first. When you increase the retarding potential, weakest electron will stop first. And the weakest in the sense, least energy. Strongest electron, which has the most energy, will be stopped at the end. Okay, so when all the electrons are stopped, energy reduces to 0. And this potential was called stopping potential. Correct? Stopping potential. So stopping potential is the retarding potential at which photoelectric current reduces to 0. Even the fastest electron is stopped. Okay, and here we got an important relation. Kinetic energy, maximum kinetic energy of that electron. Which electron stopped at the last? The electron which possesses maximum kinetic energy. So kinetic energy of that electron, the electron which stopped at the end, the electron which stopped at V0, its kinetic energy will be equal to EV0, right? This was one of the equations we have remembered from this discussion. So effect of applied potential we explained in detail because it is somehow related to so many other concepts. So 2 points, like one is accelerating potential. With respect to accelerating potential, current is increasing. Okay, right, and up to a maximum value which is called saturation current. When you increase the retarding potential, photoelectric current decreases and finally stops. That potential is called stopping potential. Then kinetic energy of the fastest electron, highest kinetic energy electron, its value will be EV0. Okay, fine. Then this is that experimental study. From this we conclude some observations which is called law of photoelectric emission, right? We get question, state law of photoelectric emission, or we have to conclude that observation we made from the experiment. What are the observations we made? First one, intensity of radiation. Correct? Photoelectric current is found proportional to intensity, or number of electrons emitted from the metal surface is directly proportional to intensity of radiation. It is independent of frequency. If you change the frequency, you cannot release new electrons. If you want to release new or more electrons, you have to increase intensity. Okay, then second observation was regarding the kinetic energy of electrons. Emitted electrons, suppose 5 electrons are emitted. If you want to make it 6, increase the intensity. Right. What happens if you increase the frequency? Those 5 electrons will be emitted with greater energy, with the greater kinetic energy, right? Yes. Okay, and when we apply the potential, when we change the potential value, we found how is it varying. Okay, so the law of photoelectric emission, first one, intensity relation, second one, frequency relation, and the third point in that law is definition of threshold frequency. There is a minimum frequency below which no photoelectric emission possible for a given photosensitive material. That is called threshold frequency, right? Yes. And the fourth point in the law of photoelectric emission is photoelectric emission is a very instantaneous process. Instantaneous process in the sense it is there is no time lag between incidence of radiation and emission of electron. Okay, so these 4 points together we call law of photoelectric emission. Okay, fine. Now that was the first part of the photoelectric effect. We study photoelectric effect, we studied experimentally and we observed so many things. Now its explanation is coming from Einstein. Einstein's explanation, we know this is where we get important equations of the chapter, and numerical questions also coming from this part. Right. So Einstein explained photoelectric emission. See, as I told you, we are trying to explain particle nature of light. That is why we picked photoelectric effect in this chapter. We have to explain, or we have to discuss particle nature of light. Light has a particle nature. Then how will we explain that? Using a phenomenon called photoelectric effect. Some of the phenomena can be explained only using particle nature of light. For example, photoelectric emission. Some other phenomena can only be explained using wave nature of light. For example, interference, diffraction, right? These kind of that we discussed in wave optics. Those concepts can be explained only using wave behavior of light, but this with particle nature of light. Okay, to explain this, Einstein introduced photon theory of light. Einstein said, the quanta of light, the quantum theory from Planck's quantum theory. Energy is transferred from one point to the other as the form of quanta, small packets of energy, right? Yes. So for light, that small packet is called photon, term introduced by Einstein. And he explained the properties of this photon. What are the properties of this photon? Photon has a they are chargeless, massless, right? We know chargeless and massless particles. Advantage of being chargeless and massless: if it is chargeless, it will be undeflected in electric and magnetic fields. If it is massless, it will be undeflected in gravitational field also. Correct? Yes. So light will not deflect when it passes through an electric or magnetic field, even gravitational field, because massless, chargeless and massless, right? Okay. And energy of a photon, energy of one photon. See, light travels as a collection of particles. Each particle is called a photon. One of the photon, each photon will have an energy which is equal to h nu, where nu is the frequency of that radiation, right? Frequency of the radiation. Suppose you are going to take a red color source. Red color source will send so many red photons. How will you find out energy of one of the photons? H into frequency of the red light. Correct? Yes. Fine. And that H, we know it is a Planck's constant. Right. And this is the energy of one single photon, or it can also be calculated as hc by lambda. Right? And we know in this modern physics part, dual nature, atoms and nuclei, in the previous life we explained the same concept. We use another equation. We have to get that energy in an electron volt, not in joules. So energy to obtain in electron volt, we have an equation. Hc is going to be 12375 or 12400, wavelength in angstrom, right? This equation will give you directly electron volt energy. Otherwise, if you substitute H is equal to 6.6 into 10 raised to minus 34 joule second, C is 3 into 10 raised to 8 meter per second, all values will be in SI unit, your energy will be in joules, but we need energy in electron volt. We have to convert that finally. Otherwise, just use this equation. Directly we will get electron volt energy, provided lambda should be substituted in angstrom, or 1240 divided by lambda in nanometer. That also we use. Okay, we know this equation. Energy of one photon we calculated like this, and all photons, all photons has the same velocity in vacuum. What is the speed of photon in vacuum? C is equal to 3 into 10 raised to 8 meter per second, and that C can be represented as 1 by root of mu naught epsilon naught, right? Speed of light in vacuum, 3 into 10 raised to 8, or speed of any photon in vacuum is 1 by root of mu naught epsilon naught. We know what is mu naught. It is permeability of vacuum. Epsilon naught is permittivity of vacuum. So speed of light in vacuum will be 1 by root of mu naught epsilon naught. In any medium, velocity of light will be, or velocity of photon will be 1 by root of mu into epsilon. We know mu naught is reserved for vacuum, epsilon naught also for vacuum. Mu and epsilon are permeability and permittivity respectively of that given medium. Okay, that is how we explain the properties of photon. They are chargeless and massless. Their speed, see, same, all the photons, irrespective of their frequency, irrespective of their wavelength, all photons has the same velocity in vacuum, and that is 3 into 10 raised to 8 meter per second, which is represented in terms of permeability and permittivity. Okay, they are chargeless, massless. Their energy can be calculated like this. So basically, at least these 4 or 5 properties you have to remember for photon, which we will use in our further discussions, right? Okay, so that was the photon theory. He introduced the photon concept. Now, before coming to this graphical representation, what was the explanation given by Einstein? Einstein explained this as a particle-particle interaction. This is a photon, one of the photon from the incident radiation. That photon incident on the metal surface, right? There will be electrons, and the electron will absorb energy from incoming radiation or incoming photon. It is a particle-particle interaction. It is not radiation. Particle in the sense photon and electron, both of them are particle. Light is no more a wave in this discussion. Light is particle, right? That was a key concept. Fine. So particle of light, photon, interact with electron, another particle. Photon kicks out electron by imparting energy. Energy of incoming photon was h nu, E is equal to h nu, we know. That energy will be given to the electron. Electron utilizes that energy for two purposes. One is to be free from the metal surface, we know, right? Atom is like connected, attracted towards the nucleus, and it has to break the bond to be free from the metal surface. So it needs some external energy. That energy is the first part, which will be equal to work function of the given metal. Yes, work function of the given metal. That much energy is required to break the bond, to be free from the surface. So from the energy obtained from the photon, one part is utilized by electron for that. If it has excess energy, remaining energy will be utilized as the kinetic energy. It will run out of the surface, run away from, like it will be just emitting out of the surface. And those electrons which has enough kinetic energy can move the distance by themselves. They constitute that non-zero current at zero potential, the one which we mentioned before. Those who has enough kinetic energy. Okay, so this is how he explained, and the equation was energy of the incoming radiation h nu will be equal to work function plus like kinetic energy, right? Yes, therefore kinetic energy of photoelectron is h nu minus work function, and we know work function is h nu naught, right? And h into nu minus nu naught. This was the equation for kinetic energy. Yes, this is called Einstein's equation. H nu minus nu naught, or h nu minus work function. That simple explanation is given by Einstein through his photon theory of light, using photon theory of light. Okay, so remember the equation. This is the only equation we have to learn. So far we got two equations. One, kinetic energy maximum of emitted electron is in terms of stopping potential. Another equation, kinetic energy of any electron emitted from the surface is h nu minus work function. Correct? Yes. Okay. Then comes to that graphical representation once again. Graph questions. I'll be just running through those graphs once again, then we'll come to the questions. Okay. See, one of the graphs we started with is the frequency graph, right? This was frequency, kinetic energy. We get questions frequently from this graph, like what will be slope of this graph? We know what is the slope of this graph, right? Kinetic energy versus frequency. We know kinetic energy by frequency will be the graph. Will be the slope. Slope is actually always y-axis by x-axis. Change in y-axis by change in x-axis. If you represent energy as h nu divided by nu gets cancelled. We will get h as the slope of the graph. Or otherwise, we can write that kinetic energy equation. Einstein's kinetic energy equation is like h nu minus work function. Correct? Standard expression for a straight line is mx plus c. What is the value along y-axis? We have value along y-axis kinetic energy, right? Kinetic energy. Value along x-axis is frequency. Is frequency here, see, value along x-axis frequency. And then what is this? M stands for slope of the graph. From this equation we can say slope of the graph is going to be h, the Planck's constant. Planck's constant. Okay, and the y-intercept, c is the y-intercept from this equation, which is w naught is the work function. So if you extend the graph until it touches the y, so you will get this value as the work function of the metal. Okay, so you may be given a graph. Threshold frequency can definitely find out from this graph, that is nu naught if you have some value given. And also, apart from that, Planck's constant can be calculated from the graph as slope of the graph, and work function is the y-intercept of the graph, right? That straight line. Fine. And the same graph will be asked in another way in terms of stopping potential. So one point you have to remember from this discussion, slope is a constant, right? Planck constant is a constant. So if I draw two graphs for two different photosensitive materials, A and B, you cannot draw like this. This is wrong, right? This is wrong because their slopes are different. If you draw two graphs in the same axis, coordinate axis here, they should be parallel to each other. Their threshold frequency may be different. Their work function may be different. But slope should be the same because slope is a constant, Planck's constant. This is for A and this is for B. This is correct. Okay, and the same graph will be asked in terms of stopping potential. Stopping potential versus frequency. Instead of kinetic energy, we are going to take stopping potential here. Okay, we had the expression kinetic energy is equal to h nu minus work function. But kinetic energy we found as E V naught before, right? H nu minus work function. So we can say V naught is equal to h by E frequency minus W naught by E. Why did I write this equation? Now you can compare this with the standard equation of the straight line, y is equal to mx plus c, just like in the previous case. This time we have value taken along y-axis, it is V naught. V naught. Yes. Along x-axis, still frequency only, no change. Frequency. Correct? And you know, the y-intercept should be W naught by E. So we can identify slope easily directly from this, right? And the graph, this graph is also a straight line because kinetic energy is E into V naught. Kinetic energy is proportional to V naught. Therefore, it should be proportional to frequency also. Kinetic energy proportional to frequency. Therefore, V naught should be proportional to frequency. The graph still a straight line, but slope will be different. And also, y-intercept will be different. This time, this is the threshold frequency, no change. But y-intercept is W naught, work function by E, not work function, right? See the difference. And slope of the graph is not h, still a constant only, but not h, but h by E, where E is the charge of electron. Okay, so this is how the graph will be changed if you take like V naught, stopping potential, instead of kinetic energy. Graph looks almost the same, there is no difference, right? So don't be in a hurry to answer your question. If you get one more question or something, what is the slope of the graph? It can be either h by E or h, right? Because the graph looks similar. Check what is the value, which is the value given along y-axis. If it is kinetic energy, slope will be h, and if it is not, if it is V naught, then h by E is the slope. Okay, so be careful. Right, and that is the one of the graph we explained, right? Fine. Then the other graph is a potential graph that also we have to explain a little, then we will come to the questions. This was photocurrent, photoelectric current, accelerating potential, retarding potential, right? We found non-zero current flowing even at zero potential applied. Some electrons had enough energy, so they crossed the distance by themselves, they constitute current, we explained in detail. And the graph was somewhat like this. There was a saturation current, and on the other side it decreases, right? And this point is stopping potential V naught. See, this is the graph we obtained from an experiment in which intensity was 1 unit, right? I am going to keep frequency as a constant. Frequency is 1 unit. I am not changing it. Only intensity let me change. If I change intensity into 2 units, what will be the difference? If I use more intensity, more electron should be coming out as per the observation, right? More electron comes out means more current will be flowing through the circuit. So even at zero potential, this time more current is flowing because we use more intensity of the source, right? So I mean of the light radiation. So the graph will be similar to the previous one, but with higher values, greater current. Saturation current will be greater, even non-zero current, non-zero potential current also, right? No, zero potential current also will be greater. So this is for intensity 2 units. Intensity 2 units, correct. Okay, then what happens if I reduce the intensity? If I reduce the intensity into, for example, half a unit, intensity reduces to half units, just for a comparative study only, okay? 1 unit and then half a unit, less than 1 unit. Anyway, so at that time it will be reduced, right? Intensity reduced, so current will be reduced. So current is varying like this. So when you look at that accelerating potential side, the graph with highest current, highest current will be the maximum intensity. The lowest current, will be the minimum intensity, because current is directly proportional to intensity. Okay, in all these 3 cases, frequency kept a constant, 1 unit. I only changed the intensity. Then you have to complete the graphs to the other side in retarding potential into the same stopping potential, not different points, because we know stopping potential is related to the kinetic energy, right? Kinetic energy is equal to EV0. If you want to get more stopping potential, kinetic energy of the electron should be more. But if you want to increase the kinetic energy of photoelectrons, not the intensity, but frequency is supposed to be changed, right? We didn't change the frequency, therefore stopping potential remains the same. All the graphs will be coming to the same point only. We change intensity, but frequency kept constant. So different values of current, same stopping potential, correct? Okay, whereas if it is the other way around, if I change only the frequency, by the time you could have figured it out, right? If I have the first case, 1 unit intensity, 1 unit frequency. I am keeping intensity a constant now. Intensity I kept 1 unit. I am not going to change it. But frequency, let me increase. This was 1 unit frequency, so V0 will be somewhere here. If I increase the frequency, will the current be affected on the other side? No, right? Current remains the same. Same zero potential current, same saturation current, but when you increase the frequency, the change will be from here onwards greater threshold, greater stopping potential V0 dash. And if you reduce the frequency than 1 unit, just like half a unit before, this will be V0 double dash. Smaller frequency, smaller stopping potential. Higher frequency, higher stopping potential. So when you look at the graph, you should be able to understand this is one single intensity, different frequency, correct? Yes. Whereas in this case, one single frequency, different intensities. Okay, fine. These are the graphs, graphical questions, and directly we get a question from that part here. Let's go through the question. Figure shows a plot of 3 curves A, B and C showing the variation of photocurrent versus collector plate potential. Collector plate potential is accelerating potential, okay, applied potential basically. Yes, for the 3 different intensities I1, I2 and I3. I1, I2, I3. Having frequencies nu1, nu2 and nu3. Okay. Respectively, incident on a photosensitive surface. Okay, the question is to identify the graph with same frequencies. Okay, question number 1, same frequencies, the graph for same frequencies. And the second one, I'll add one more question into it. Which frequency, which relation is like, how can you relate the frequencies? Not frequencies, relate intensities, correct? Yeah. So you have to identify the 2 graphs which is given for same frequencies. Which are they? Yes, for frequencies, exactly. 2, I2 and I3. They are named like A, B and C. So you can answer according to that, like A, B and C. 3 graphs are given. Out of them, 2 of them are for same frequency. It is obviously from this, stopping potential is the same for A and B, which means frequency of the graph A is equal to frequency of the graph B, right? So same frequency graphs are A and B. Right? A and B. How do you know? They have the same potential, same stopping potential. So they should have same frequency of incident radiation. Yes. Now, the second question was how to relate these intensities. How will you relate the intensity? Which is the highest, in the increasing order I will go. Then we know I3 is less than I2 is less than I1. Right? Yes. So highest intensity for maximum current, lowest intensity for minimum current. That's the relation of intensities. Okay. So different intensity, different frequency, but A and B are for same frequency. Yes. Okay. Hope you got it. We explained the same thing in the graph. Sorry. Yeah. Now look at the next one. The graphs drawn here are for the phenomenon of photoelectric effect. We know. Yes. Identify which of the two characteristics, intensity or frequency, right, of incident light is being kept constant in each case. You are given two graphs. Easy for us. We already explained, right? Which is kept constant? Can you tell me what? This is the graph 1. In graph 1, which is kept constant? Frequency or intensity? In the first one. And look at the second. You have to keep, you have to check which quantity there, either intensity or frequency. Yes. Yeah. First one, we know intensity kept constant. Here intensity constant. Exactly. Yes. Because different frequencies, different work formula, like stopping potential, but same current value. And look at this. In the second graph, frequency kept constant because same stopping potential but different values of current, right? Intensity I1, intensity I2, intensity I3. Highest frequency is I3, more current. Okay, so it is easy now, right? We know how to select or how to identify which parameter is kept constant. Yeah, exactly. Next question, again from the graph. Figure shows variation of stopping potential V0 with the frequency nu. Okay, that is nu for two photosensitive material M1 and M2. You can see the graph. See, look at the graph. M1 and M2 given straight lines with equal slope. Why is the slopes same for both lines? Yes, exactly. We know h is the slope of the graph, right? Slope of the graph is h, which is a constant, Planck's constant. So you cannot draw the graph with different slopes. I explained this with an example before. So the slope of the graph should be same because for v, not h, sorry, h by e, because look at the value given along y-axis. This is what I told you. Yes. It is V0, stopping potential. If it is stopping potential, slope is not h, it is h by e. Right, still a constant. Fine. Therefore, first question can be answered. Slope of the graph is h by e. Both h and e are constant. So whatever may be the photosensitive material, slope of the graph should be the same. Now, for which material will the emitted electrons have greater kinetic energy for incident radiation of the same frequency? Justify your answer. Second part is to identify which material will emit electrons with greater kinetic energy. Electron with greater kinetic energy, M1 or M2? Yes, Faiz. Yeah, flip-flop. Welcome back. Okay, Dravil. Yes, Sania. Yeah, all of you are getting the correct answer only. M1 emit electrons with greater kinetic energy. And why? You are asked to justify your answer. Justification is, we know kinetic energy is equal to h nu minus work function. Right? Work function is W. Which of the metal has smaller work function? M1 has work function W1, suppose M2 has work function W2, then W1 will be less than W2. Why? Threshold frequency of M1 is less than that of M2. So smaller work function. If work function is smaller, small quantity is subtracted from the incident radiation energy, then kinetic energy will be greater, right? If W0 is smaller, kinetic energy will be greater. So we can say work function of M1 is less than work function of M2. So from this equation, kinetic energy of 1 should be greater than kinetic energy of 2. So M1 yield electrons with more kinetic energy than M2. Okay, fine. Yeah, and we are coming to the last part of that chapter, which is de Broglie hypothesis. We don't have much things from this part, especially we have some deleted portion from this side. De Broglie wavelength of electron is the only equation we have from this side. Okay, so de Broglie hypothesis we know. Here we explain particle wave nature of matter, right? Wave nature of particle. In the first part, in photoelectric effect part, we explained particle nature of light, Einstein's particle nature of light. And de Broglie all of a sudden came up with one hypothesis. It is called de Broglie hypothesis, right? Not de Broglie's law. He has some like wild imagination. He was just assumption. That is why it is called hypothesis. And later someone proved it experimentally. That is why we study so many hypotheses were there, right? But we didn't learn all of them. De Broglie hypothesis is taken because this man was damn right. And wave nature of particle, he explained, if you have a particle, see, his argument was a little funny. Like Einstein explained particle nature of light. Light can behave like a particle. So he thinks like why a particle can't act as a wave. Why? That he says nature loves symmetry. So if wave act as a particle, particle should act as a wave. And he had some mathematical proof for that. He explained if a particle has a mass m, it is converted to energy, then according to Einstein's mass energy equivalence, this much energy will be released. This energy is coming out in the form of a radiation of frequency nu, then that mc square can be equated to h nu. This was his concept. Correct? Particle is converted to energy. Yes, and he kept mc here, h nu by c, taken c, one c to the other side. Mc is mass into velocity, which is taken as momentum, and h by lambda, because we have c is equal to nu lambda, right? Nu by c is equal to 1 by lambda. That lambda is taken here. And in this equation, lambda is equal to h by p. This man beautifully connected two important properties. Like lambda is property of a wave. Wavelength is a property of a wave. Momentum is the property of a particle, right? Mass into velocity. We cannot imagine momentum for a wave, usually, right? Yes, so lambda and p, he connected very beautifully. So it was not just an imagination. He had some mathematical proof, but he couldn't prove it experimentally. Someone else did it. Okay, this was the de Broglie's hypothesis. And from this part, only one equation, and even its derivation is not there. Derivation is deleted. Lambda E, wavelength of electron. Right? To obtain that, we have lambda is equal to h by p, de Broglie hypothesis, and that is written as h by like momentum kinetic energy relation we know 2me, where E is the kinetic energy, root of 2me. Momentum is equal to root of 2me. Yes, and that lambda is equal to h by root of 2m into qv, where v is the accelerating potential. When you accelerate a charged particle across a potential v, it gains kinetic energy. Okay, we know all these equations before also. Electrostatics. Okay, h by root of 2mqv. Correct? So for an electron, h by root of 2 into mass of electron and E, charge of electron, into V. Correct? Yes. He predicted electron will have a wavelength which is equal to, see, h is a constant, 2, mass of electron, charge of electron, everything constant. He found 1.227 root of V nanometers. This could be wavelength of electron if it is accelerated through a potential difference of V. V can be anything. So that's a variable. We simplified everything else. Okay, and this was experimentally proved later by Davison and Gerber, which is a deleted portion for us. And this is the end of that dual nature of matter and radiation. That is done. I think we have one or two questions from de Broglie part also. Let's go through that. Question number 1. De Broglie wavelength of particle of kinetic energy K is lambda. Wavelength is connected to kinetic energy. That is why I gave you the other equation, right? Momentum kinetic energy relation we replaced. Okay. Then what will be the wavelength of particle if kinetic energy is k by 4? It's an easy question, we know. See, we have the wavelength lambda is equal to h by root of 2m e, right? This is the equation. It was lambda. Now what happens? Kinetic energy changes to k by 4. Okay, E is taken as k here. So I can say this will be 2mk, right? 2mk. Then if you change the kinetic energy into K by 4, H by 2 root of M into K by 4 will be coming in the denominator, right? K by 4. You are asked to find what is lambda dash in terms of lambda. That's it. You can take the ratio. When you take the ratio, what will you get? Lambda by lambda dash is equal to H, 2, M and K will be cancelled. See, 1 by 4 is there. It comes up, correct? And we get root of, it is inside the root and we will get 2. So what will be lambda dash? Lambda divided by 2, half of the previous value. Just direct substitution only. Okay. Yes. Okay, fine. Moving on to the next. Work function of substance is 4 electron volt. The longest wavelength of light that can cause photoelectron emission from this substance approximately. See, they are simply trying to confuse you by introducing these kind of things. So don't be distracted, don't be confused. This time you are asked to find what is the longest wavelength. Longest wavelength is actually shortest, right? Like smallest frequency. Longest wavelength is the smallest frequency. They are actually talking about threshold frequency. But you are not asked to calculate threshold frequency. You have to calculate threshold wavelength, lambda naught. Yes, threshold frequency is the lowest possible frequency for photoelectric emission. But wavelength will be longest at that time. Correct? Smallest frequency, longest wavelength. So you are given work function in electron volt. It is E is equal to 4 electron volt. Energy is given. That is a work function actually. So the minimum energy of the radiation should be how much? 4 electron volt. That's the meaning of work function. At least the incoming radiation should have an energy 4 electron volt. Then what will be wavelength of that particular wave, that radiation? That is the minimum, right? I mean longest, maximum wavelength possible. So we can say E is equal to Hc by lambda. We know this equation and we have been using this in like other chapters too. 12400 I told you before, divided by what is the wavelength given? That is to be calculated. Yes, lambda. Remember, it will be obtained in angstrom. What is energy given in electron volt? 4 electron volt. So we can say 4 is equal to 12400 divided by lambda in angstrom. So what will be lambda? Lambda in angstrom 12400 divided by 4. Yes. So what will you get? If you cancel this, you will get 3100 angstrom, right? 3100 angstrom. And you are given all the values in nanometers, so we can take D as our option, right? 310 nanometer is 3100 angstrom. Yes. So longest wavelength, smallest frequency. That was the hint, threshold frequency, right? So the incident wave radiation should have a minimum energy at least 4 electron volt. Then corresponding wavelength should be 310 nanometers. Okay, fine. So I think that was the last question from yeah, one more question. Figure shows a plot of root of V. Okay, 1 by root V. Are you able to see that properly? 1 by root of V. That is the term here. 1 by root of V, where V is accelerating potential versus de Broglie wavelength lambda. In the case of two particles having same charge Q but different masses M1 and M2. Which line A or B represent a particle of larger mass? Okay, question from wavelength of electron part. Okay, de Broglie wavelength of electron. We have the de Broglie wavelength of electron lambda in terms of like accelerating potential. That is what we have to consider for this. Along y-axis you are given 1 by root of V. V is the accelerating potential. Okay, lambda is along x-axis. These are the two different particles. The question is which particle has greater mass? Okay. How can you connect that mass with this graph? That is what the only thing you have to do to find the solution. Okay. First of all, we'll start with lambda expression, h by root of 2m into qv. I'll go for this equation because The graph is in terms of accelerating potential. So de Broglie wavelength is h by root of 2mqv. Okay, it is given that masses are different but charge is the same. So we can say h will be same for both particles, 2 is a constant, same for both. Charge is also same as per the question, same charge q, but mass is different, right? So we can say only m and v are variables. We can say lambda is proportional to 1 by root of m into v. 1 by root of m into v. Okay, what will be lambda into root of v here? It is proportional to, it is directly proportional to 1 by root of m. Okay, remember this term. Now we connected wavelength and accelerating potential with mass somehow. Now look at this. What will be slope of this graph? Slope of the graph. We know it is y-axis by x-axis. So we can go for 1 by root of v, that is y-axis, divided by x-axis value is lambda. Correct? Yes. So what is the slope? Slope of the graph is going to be 1 by lambda root v. Correct? That is why I calculated lambda root v here before. Slope of the graph is 1 by lambda root of v. Okay, what next? We can say slope of the graph is 1 by lambda root of v, and lambda root of v is proportional to 1 by root of m. So we can say slope is proportional to 1 by lambda root of v, which is proportional to root of m. How do you know? Slope is 1 by, right, lambda root of v only, but lambda root of v is proportional to 1 by root of m. So 1 by lambda root of v will be proportional to m. The conclusion is slope is directly proportional to root of m. Correct? Now you can identify the particle with greater mass by looking into the slope. Slope of the graph is proportional to mass, root of mass actually. Okay, so greater slope, greater mass. Okay, so we found out the slope from the graph, and that was something. Then from the equation for de Broglie wavelength of electron, we found out the same quantity and we compared them. Okay, so slope is greater for A, so A has greater mass, correct? A has greater mass. Okay, it is given as M1 and M2. So M1 is greater than M2. M1 for A and M2 for B. Okay, I hope it is clear. Yeah, yes. Exactly. This, if you have to find out numerical value, you cannot do this. Since we have to go for the ratio only, I have taken the ratio like this. We have taken the constants. That is how we formulate a like relation. Easy to proceed. Otherwise, you have to keep all the constants. It's obvious. Exactly. Fine. So that's it from the dual nature of matter and radiation. We are actually running out of time. Now, atoms and nuclei. 2 chapters which we revised before, like for MCQs. Will be just go through the important concepts, and I'll tell you which are the topics you have to concentrate for long answer questions first. Then we will do some sample questions and we'll proceed. Okay. Right. So atoms, like dual nature. This is also a small chapter. The backbone of the chapter is Bohr atom model. Just we have to understand Bohr atom model properly to answer all the questions from this chapter. Any question, whether it is long answer derivation questions or numerical questions, whatever it may be, you should know Bohr atom model properly. So that is the very important concept in the chapter. To reach Bohr atom model only, we introduced Rutherford atom model. Okay, alpha particle scattering experiment, we know, right? Okay, so we have some 1 or 2 points or parameters to remember, understand from Rutherford experiment, then Bohr atom model. In Bohr atom model, we will derive expression for orbit, radius of the orbit. This is possible for a long answer question, derivation of orbit, okay? Derivation of orbit, and velocity of electron in an orbit using Bohr atom model. Bohr postulates, we derive velocity of electron in an orbit. that derivation is actually deleted. We don't have that velocity, so don't worry about it. Just understand what happens to the velocity when it changes the orbit. We will just mention that later. Energy of energy level, this is another possible long answer question. Okay, we know kinetic energy we calculate, potential energy we calculate, then sum of the two will be the total energy. Okay, so that is how we found energy of energy levels. These two are important derivations. Okay, long answer questions, you should learn these two. Fine. Atomic spectra derivation, also the new syllabus, revised syllabus for us, it just says qualitative treatment is enough. So we hope that derivation won't be coming. So long answer question for these two. Yes. And in dual nature of matter and radiation, I forgot to mention that these three factors, you know, how intensity, frequency and applied potential affects photoelectric emission. That has a potential of 3-mark question. Okay. So just understand, or just prepare, just learn that properly. If we get a 3-mark question to explain the graph and their relation, you can write in detail. So for 3 marks. Apart from that, we don't have any new long answer question from dual nature of matter and radiations. Okay, fine. Then the last part of the chapter, Bohr model of hydrogen atom. In Bohr model of hydrogen atom also, we have that energy level treatment. That energy level is the very important concept. When I showed you in the last live, when we discussed this portion, I showed you that weightage or the percentage wise, which portion is important from the previous papers. So one of them was energy levels, correct? Energy levels and the transitions like atomic spectra. So that part was very, very important, and we get numerical questions mostly from that part. Long answer questions, this can be from these two, radius or energy level. Okay, fine. Rutherford atom model, we will just mention that just to bring that two concepts, like what is impact parameter, right? Impact parameter is important because that particular concept gave a physical approach to this experiment. Rutherford was trying to explain it more physically, charge interactions, right? Not chemically, it is more physical, right? Physical concepts, charge interaction. For that he introduced it, impact parameters. And I'm not going to Rutherford experiment in detail. We all know that when he sent alpha particle to a gold foil, and most of the alpha particles are, they passed through the gold foil undeviated, around 99%, right? Yes, more than 95, around 99% passed through the gold foil undeviated. But that was not the expected result. See, before that there was Planck pudding model, J.J. Thomson, which suggests atom is a completely filled sphere. There is no gap for alpha particle to pass through, to penetrate through. But observation was just the opposite. Most of them, around 99% of alpha particle went undeviated, and some of them deviated with small angles, very few deviated by 180 degree, right? Just bounces back. And that probability is like 1 by 8,000. When you send 8,000 of alpha particles, like one of them rebound. Okay, anyway. Importance of impact parameter, physical significance of impact parameter. Impact parameter is a distance, right? This is nucleus in the gold foil, gold nucleus. Alpha particle is passing through the gold foil. Both of them have positive charge. Alpha particle has a positive charge. Alpha particle is a combination of 2 protons and 2 neutrons, we know. So it has positive charge. All the positive charge is concentrated at the center of the nucleus, and that is, the nucleus has a positive charge. So this alpha particle, when it approaches the nucleus, what happens? Repulsive force, right? That is what I told you. He is explaining it more physical, right? Physical concepts like charges are interacting. Positive charge and positive charge. There will be a repulsive force, because of which this alpha particle is expected to deviate by an angle theta. That is called the angle of deviation or scattering angle. Fine. Then we defined impact parameter as a distance between 2 straight lines. Which are the 2 straight lines? The first straight line is the initial direction of alpha particle, the green line, which you can see on the board. And the second one, a line parallel to that and passing through the center of the nucleus, right? Yes, this distance was called impact parameter. Then how did he explain his observations through, using impact parameter? He said, if B is large, If impact parameter is large, what do you mean by that? If impact parameter is large, all alpha particles are passing far away from the nucleus. Impact parameter large means alpha particle are passing along a line which is far away from the nucleus. If B is large, theta will be 0. There is no angle of deviation, it won't be deviated. Okay, fine. Then if B is small, what happens if B is small? If B is small, there will be some deviation, right? Theta is not equal to 0. There will be some deviation. Some of the alpha particles are found deviated. Yes. And if B is equal to 0, if B is equal to 0, what happens? The alpha particle is supposed to pass along this line, then only B is 0. And at that time, theta is going to be 180 degree. This observation he used to explain, or he used to conclude size of the nucleus is negligibly small, because 99% of alpha particle had large impact parameter. They passed undeviated, correct? Which means they didn't get a chance to meet the nucleus at all. They didn't feel the presence of nucleus at all. So nucleus is negligibly small. That was a conclusion. So majority of the space inside an atom is empty, so that 99% of alpha particle couldn't find a nucleus inside it. They didn't feel the presence of nucleus when they passed through atom. Okay, based on that, he formulated his atom model, right? Yes, and that atom model had some drawbacks. He suggested, or he contributed the concept of nucleus into the atom models, right? That was a very important turning point. Okay, then followed by this, we get Bohr atom model. What was the drawback of Rutherford atom model? We know the stability issue, right? Rutherford couldn't explain the stability because in electromagnetic waves we explained that, like, accelerated electrons emit radiation. According to Rutherford atom model, electrons supposed to revolve around the nucleus. Electrons revolve around the nucleus are examples of accelerated electrons, right? They have a centripetal acceleration. All accelerated electrons emit radiation, energy. They emit energy. When they lose energy, these electrons will come and collapse in the nucleus. Atom should not exist. Atom should not be stable, according to Rutherford atom model. Okay, so this man Niels Bohr was trying to overcome that particular problem. He want to fix the orbits. Orbits are not varying its radius. It is going to be fixed. And the three postulate of Bohr atom model, that is the only thing you have to remember from this chapter. All your long answer questions, the one which I mentioned in the beginning, both of them, I told you two of them, right? Yeah, both you can derive easily if you know what are the postulates of Bohr atom model and its mathematical representation. It is easy to remember also. First postulate, we know Bohr says that electrons are revolving around the nucleus in non-radiating orbits using electrostatic force as the necessary centripetal force. For every circular motion, body should possess some centripetal force, right? That centripetal force is provided by which force? Electrostatic force. So first one is mv square by r is equal to k into q1 q2 by r square. Electrostatic force between nucleus and electron. If electron revolves around the nucleus, it is attracted towards the nucleus, right? That is the electrostatic force we are talking about. That force acts as a centripetal force. Centripetal force can be calculated as mv square by r, where r is the radius of the circular path. K q1 q2 by r square. We know k is 1 by 4 pi epsilon 0. We'll substitute this later. q1 is charge of electron, which is E. One of the charge in that pair is electron, so E. The other charge is nucleus, right? Force between electron and nucleus. Charge of nucleus is equal to Z times E, meaning Z is the atomic number of the nucleus. Atomic number is the number of protons inside. That many protons will be there. Each proton has an energy, charge E. So Q1 and Q2 will be these values. One of the R gets cancelled. We get mv square is equal to K into Z E square by R. Equation number 1. If you know this equation, believe me, the first 3 mark question is done. You know how to derive it. Yeah, just remember the mathematical form of this first postulate. mv square is equal to kz square by r. Yes. What happens if I multiply with a half here? Half mv square is what? Kinetic energy. Yes. Yes. You directly get kinetic energy. You have to multiply 2 here also. Then, it's balanced. Kinetic energy expression here, kinetic energy of electron in an orbit. We'll come to that later. Okay, anyway. This is the first postulate number 1. Whenever I am talking about first postulate of Bohr atom model, this equation should come to your mind. mv square is equal to kZe square by r. Okay. Now, the second postulate is about angular momentum, right? Angular momentum of electron revolving in an orbit is integral multiples of h by 2 pi. L is equal to nh by 2 pi. He was trying to fix the orbit. I told you that was his prime objective. He has to overcome that varying orbit problem. He has to overcome that stability problem. So if an electron is revolving in an orbit, such an orbit is possible only if angular momentum of electron, which can be written as mvr, m mass of the electron, v velocity with which the electron revolves in the orbit, and r is the radius of the orbit. An orbit is possible only if that mvr is equal to nh by 2 pi. See, second postulate, mathematical expression, done. You learn the second postulate also. Okay, these representation is enough. You can write the statement if you want, and you can use this for the derivation directly now. Okay, so for the first radius, n should be 1. N is the number of orbits. For the second radius, if you want to calculate r2, put n is equal to 2, and so on. Second postulate. And the third postulate was regarding energy levels, right? Energy levels. Bohr called each orbit an energy level. He was trying to oppose, he was trying to block that varying orbit case, right? But he says electron can come closer to the nucleus, it's okay. Electron can go away from the nucleus, that's also fine, but not by themselves. They are not simply coming to the nucleus and colliding, collapsing, not like that. If you want to bring the nucleus, electron towards the nucleus, the electron should emit some energy, because each and every orbit possesses some definite amount of energy, right? First orbit will have, suppose, 1 electron volt energy. Second orbit possesses some energy. Third orbit possesses another energy, suppose, in this way. Therefore, each orbit is called an energy level. Okay, that energy level was they have definite energy. So an electron which has 1 electron volt energy can revolve only in the first orbit. It cannot go to the second because its energy is not matching. It cannot go to the third. An electron revolving in the second orbit cannot come to the first. It cannot go to the third because their energies are not matching. But if this electron has to go back to first or come back to the first orbit, it can emit 1 electron volt energy and coming back, right? That we know. Releasing energy, making it 1 electron volt, coming back to the first, or absorbing 1 electron volt, going to the third energy level, and so on. For that, according to Bohr postulate, energy to be absorbed or released. If electron is coming to the lower energy level, it should release energy. If it is going to the higher energy level, it should absorb energy. That energy difference is, EF minus EI. Energy of the final orbit minus energy of the initial orbit. Each orbit has an energy, right? So that energy difference, how much is that energy difference? That much energy should be either absorbed or released based on the transition. That was the third equation. Bohr atom model is done. If you are okay with the Bohr atom model, forget atoms. That is under control. I told you we have 2 long answer questions. Derivation of radius and derivation of energy levels, right? Energy of different orbits. Both can be derived very easily if you know postulate number 1 and 2 mathematical form. Okay, I'll just show you simply what we are going to do for expression for radius. Okay, in the radius part, we are going to take the first postulate. First postulate was mv square, right, is equal to k into ze square by r. This was the first postulate. I told you when I talk about first postulate, this should come to your mind. R is equal to k ze square divided by mv square. Done. This is expression for radius. But this v is a variable. See, velocity will not be same in all radius. It will be different in different orbits. So we have to replace that V using the second postulate. What was the second postulate? mvr is equal to nh by 2 pi. So we take V from this. V is equal to nh by 2 pi m into r. You can substitute that for V. Then your radius expression is done. It is difficult to remember these equations because so many terms, so many powers, but in 2 steps, look at this, literally 2 steps, you can derive what is expression for radius. R is equal to, see, k z e square divided by m into velocity square. Velocity square in the denominator, it becomes n square h square divided by something, it will go up, right? That will be 4 pi square m square r square, because v square, this term should be completely squared. Now look at this, our equation should be transposed like, because r is cancelling from one side. So you have now just rearrange the equation. R is equal to, we will get m into, see, one of the m gets cancelled here, so m is not there, n square h square, the whole divided by k z e square 4 pi square m, only m, right? That's it. Just substitute k is equal to 1 by 4 pi epsilon 0. Done, finished. If you substitute k value as 1 by 4 pi epsilon 0, as I told you before, you will get the final answer. So radius derivation is pretty easy. We get the question either to derive expression for radius, or it may be like r proportional to n squared. Just show that radius of an orbit is directly proportional to n square, and it is clearly visible in this equation. R is directly proportional to n square because h is a constant, k 1 by 4 pi epsilon 0 constant, z is constant for a given atom, yes, z is atomic number, e electron charge 4 constant, pi constant, mass of electron, everything constant. R proportional to n square. Okay, that was the expression for radius. Okay, don't by heart the equation, just remember to derive, that's it. Energy of energy levels. How will you find out energy of energy levels? See, we have again the first postulate. This long answer question will be sometimes like derive expression for kinetic energy and potential energy of an electron revolving in an orbit, and hence obtain energy level, I mean energy of any energy level. So energy of any energy level is actually sum of kinetic and potential energy of the electron revolving in it, that we know. Why electron possesses some kinetic energy? Because it is revolving around the nucleus, it is moving around the nucleus, kinetic energy. Why it possesses some potential energy? Because there is a electrostatic potential energy, there is an electrostatic force acting between nucleus and electron, attractive force, there will be potential energy. So then kinetic and potential energy values, if you know, directly you can substitute and add them, that will give you energy of the energy level. Good. See, again, first postulate, we can go to the first postulate. I gave you a glimpses of that right in the beginning when we did this, like in the first postulate, mv square is equal to k z square by r. Kinetic energy is half mv square, multiplying with half, done. Multiplying with half to balance that, multiplying with a half on the other side. We get kinetic energy of electron revolving in an orbit, k into z square by 2r. Equation number 1. One form of your energy, correct? One form of that kinetic energy. Another form of this equation, by substituting k is equal to 1 by 4 pi epsilon 0, correct? Electrostatic constant 1 by 4 pi epsilon 0, and r, radius expression. Radius expression we derived here, right? That value you have to substitute. If you substitute those two, you will get another form of this equation, and that equation, that form will be, kinetic energy has another form, which is m e raised to 4 z square epsilon 0 square n square h square divided by 8. See, this is another form of the same equation. What is the difference? We substitute for k and, sorry, I forgot to write a r here, k and r. So substituting k and r, you will get this equation. Yes, that is why I told you derivation is very easy if you remember the mathematical form of the postulates. Don't try to by heart this, it requires a lot of space, so many terms, so many powers. Okay, kinetic energy is ready. Now how will you find the potential energy? We have nucleus which has a positive charge, right? Q1, which is Ze. Electron is revolving in the nucleus, around the nucleus, and it has a charge minus E. Electron has negative charge. We are going to calculate potential energy. We have to consider the sign. Okay, U equals to K Q1 Q2 divided by R. Right, Q1 is what? E. Q2 is, Q1 is minus, Q1 is Ze, Q2 is minus E. Yes, U is equal to K into minus E Ze divided by R. And that equation is going to be minus K Ze square by R. Equation number 2. Yeah. No. Which frequency you're asking me? I missed it, I think, that chat. Sorry, guys. I was not checking the chat. So many questions are there. Okay, fine. Yeah, that's why I told you. Long answer questions, that radius and energy level question. Sorry, I'll be keep looking now, okay? Just please ask me now. I'll check the chat. Fine. U is equal to minus K Ze square by R is a potential energy equation. If you substitute for K and R just like in the previous case, we can say, yeah, U is equal to like K is 1 by 4 pi epsilon 0, R is the previous value. We get M e raised to 4 Z square with 4 epsilon 0 square N square H square with a minus sign. Potential energy is negative. Force between them is attractive. So potential energy will be negative. Yes, Jad, that frequency, right? Wave number question, wave number expression you're asking me. Syllabus says it is only qualitative treatment. So it is easy to derive, right? And when we come to hydrogen spectrum also, there also syllabus says it is only qualitative treatment. So that derivation is not expected to come. Only the final equation is written. Yeah. Yes. So U is equal to this much. Equation number 2, another form. Now, how will you find the total energy? Total energy of energy level is kinetic plus potential energy. So we get kinetic energy was K Z E square by 2R plus minus K Z square by R. Correct? So what is the result? K Z square by R is common. 1 by 2 minus 1, right? Only 2 is excess here. There is nothing here. So 1 by 2 minus 1 is going to be minus 1 by 2. So K Z E square divided by minus 2R. This is the energy of energy level. Final energy. And this expression, by substituting K and R, you will get energy is equal to M e raised to 4 Z square divided by 8 epsilon 0 square N square H square with a minus sign. Final energy, total energy is minus. Potential energy is also minus, but kinetic energy is positive. If you check equations 1, 2 and 3, that ratio you can see. Kinetic energy, potential energy and total energy. What was the kinetic energy expression? K Z E square by 2R. What is the potential energy equation? K Z E square by R with a minus sign. And what is your total energy En? K Z E square by 2R with minus sign. Done. What is the ratio? Kinetic energy, if you take kinetic energy as 1 is to, see this ratio, kinetic energy is to potential energy is to total energy ratio is equal to, but if you take kinetic energy as 1 unit, if you multiply kinetic energy with a minus 2, you will get potential energy, correct? If you multiply with the minus 2, 2 gets cancelled, the minus sign retains. 1 is to minus 2. Final energy is just multiply with minus 1. 1 is to minus 2 is to minus 1. Advantage of having this ratio, if you know any of the energy, kinetic energy, potential energy or total energy of an orbit, of an energy level, you can cancel, you can find out the other. 1 is to minus 2 is to minus 1. Okay. The same ratio will be obtained if you compare the other set of equation. I told you kinetic energy is equal to mz square e raised to 4 divided by 8 epsilon 0 square n square h square. Potential energy is equal to minus mz square e raised to 4 4 epsilon 0 square n square h square, and final energy level En is minus mz square e raised to 4 8 epsilon 0 square n square h square. See, same ratio will be obtained. They are same equations only the difference is we substituted for k and r, that's it. Then we will get this format. Yes, Dhruvil, especially when we get like 1 mark questions, or MCQ questions to compare the ratio or something. If r is going to be just 2r, sometimes the radius is doubled. What happened to the kinetic energy? What happened to the potential energy? That kind of questions this equation will be helpful than this. Yes, Dhruvil. Yeah, that's what I told you. For MCQs, we can use that directly. Yes. Okay. That is the total energy. Then atomic spectra, this is where I told you that derivation is not important. Atomic spectra, we have, okay, before going to atomic spectra, this equation we simplified. No, final energy, En. Look at this, mass of electron, atomic number, charge of electron, 8 is a constant, epsilon 0, H, all of them are constants. So we simplified all those constants and we got En is equal to Z square into minus 13.6 divided by n square EV. We retained only Z and N in that equation because Z will be different for different atoms and N will be different for different orbits in one single atom itself. Okay, so Z square by N square, everything else simplified into minus 13.6 electron volt. That is how we got this equation. Okay, fine. Then atomic spectra. Atomic spectra is like when electron excite from one orbit to the other, or it comes back, de-excite. There is exchange of energy according to the third postulate of Bohr atom model. Delta E is E2 minus E1, right? Or EF minus EI. Energy final minus energy initial. That delta E is EF minus EI. Here delta E can be h nu, right? That energy can be either absorbed or released in the form of radiation. Therefore, what did we do? We equated that delta E with energy of the radiation. Then EF and EI. EF and EI are energy levels, final and initial. We already have seen what is the energy level equation, energy of the energy level equation. We know m z square e raised to 4 by 8 epsilon 0 square n square h square. If it is final energy level, to indicate that, just put a NF minus, of course. Minus, one more minus, right? Because final energy was negative. Divided by 8 epsilon 0 square n I square h square. This is how we found it. Then the second, look at the second term, minus and minus, right? So it becomes plus. So we'll take that term first. M z square e raised to 4 epsilon 0 square 8 also, then h square. These many terms are common. Then this term become plus, minus and minus become plus. So 1 by ni square minus, this is still negative, 1 by nf square. This was the beginning of that equation. Okay, then I'm not going to the full derivation because it is not required. Here we found h nu, then we have taken the h to the other side, so it becomes h cube. Then we found nu by c, which is 1 by lambda, right? That 1 by lambda. That 1 by lambda was like m z square e raised to 4 divided by 8 epsilon 0 square h cube into c into 1 by ni square minus 1 by nf square. That equation finally simplified into 1 by lambda is equal to z square r 1 by ni square minus 1 by nf square. This is the final equation that we need to explain hydrogen spectra later. So only this final equation you have to remember, that R is called the Rydberg constant, 1.097 into 10 raised to 7 meter inverse. That was the Rydberg constant. Okay, so this simplified, this simplified form you have to remember, qualitative treatment, that is what they mentioned. Now, that is the Rydberg equation followed by Bohr model of atom. The last part of that atom chapter, it is like Bohr model of hydrogen atom. Bohr model of hydrogen atom, the only thing you have to do in all the equations you derived, you substitute Z is equal to 1. The simplest, lightest element we are going to test, right? We are going to apply Bohr atom model into that. So in all equations, Z is gone. So your R expression will be some constant into n square. Right, and this constant was found to be 0.529 angstrom, right, into n square. So first radius of the first orbit, r is equal to r0 n square is the equation we got. R1 will be equal to, when n is equal to 1, 0.529 angstrom. Second radius r2 will have a radius 0.529 into 2 square, that is 4. R3 will be 0.529 into 9, 3 square. R4, radius of the fourth orbit will be into 16, 4 square, and so on. Okay, that is one equation you have to remember. We get questions based on this radius expression. So we won't get numerical questions with that long equations, like, the big equations. But that ratio is required. We get, most of the time we have to find out the ratio from the question. And simplified form of radius. See? Okay, that was the radius concept from hydrogen atom. Then energy level of hydrogen atom, En. We had Z square by N square into 13.6 electron volt. That just simplified into minus 13.6 divided by N square electron volt. Energy level of hydrogen atom. For hydrogen atom, Z is equal to 1. So for ground state, it will be 13.6 electron volt. First energy level. Hydrogen, that N is equal to 1 is the ground state, right? Second energy level, N is equal to 2. That is 13.6 divided by 2 square, 4. Then N is equal to 3. 13.6 divided by 9, right? N is equal to 4. 13.6 by 16. And so on. I told you to remember these values. First one is minus 13.6 electron volt. Second one is minus 3.4 electron volt. Third one minus 1.51 electron volt. Fourth energy level is 0.85 electron volt. Minus, all of them will be minus. Total energy is negative, we know. So these values, if you remember, like in most of the numerical questions, it will help you to understand at least which transition we have to go for. Hydrogen atom, these are the energy levels, right? Okay. And followed by this, we had hydrogen spectra. Hydrogen spectra also explained using that Rydberg equation. In Rydberg equation, we had Z square into R, 1 by Ni square minus 1 by Nf square was the equation, right? That is 1 by lambda. Here Z is equal to 1, hydrogen atom. And we found electrons excited from the ground state, like N is equal to 1. When they are coming back to the initial level, they produce a series, Lyman series. I'm not going to explain this again because we learned in 11th and now we learned again in 12th in physics. So I hope this will be pretty easy for you. Lyman series, then if they are coming back to the second orbit, it is Balmer series, then Paschen, bracket, fund, we know. And the point you have to remember here, the way how we get questions from this part is like how to find out minimum energy transition and maximum energy transition. Wavelength of minimum energy transition. Minimum energy transition is like the nearest, if it is Lyman series, second to first is the least energy transition. Least energy transition can be least frequency transition, most wavelength transition. Okay. Then highest energy transition is from infinity to N is equal to 1 for Lyman. Upper limit of Lyman, highest frequency, and that will be the lowest wavelength. Okay, right. So most frequency is also equal to least lambda. For that, infinity to 1 for Lyman. If it is least frequency and most wavelength, highest wavelength, then 2 to 1. Okay, so this is the way how we have to find highest and lowest transitions in all. Like if it is for Balmer series, lowest energy is from 3 to 2, nearest to the initial, 2, right? 3 to 2. It will be 3 to 2. And highest energy will be from infinity to 2. Here, lowest energy from 4 to 3. Highest will be infinity to 3, like that. Okay, and in all those transitions, in all those calculations, we get 1 by r, right? So 1 by lambda is equal to r into 1 by ni square minus 1 by nf square is the equation. If you want to find lambda, finally the RHS, you have to take the reciprocal. When you take the reciprocal, r will be in the denominator. And we know r has some weird value, 1.097 into 10 raised to 7. Dividing by that is, we don't like that kind of calculations, right? Yeah, and that is why I told you on that day to remember 1 by r also. 1 by r is going to be 0. Anybody remember that value? Let me check. Reciprocal of r. In all these calculations, when you want to find lambda finally, we have to take the reciprocal. Okay, and that value was 0.911 into 10 raised to minus 7. Yes. Yeah, 1 by E, then 1 by epsilon 0, 1 by R. These values, if you remember, it will be easy. Epsilon 0, R values will be given in the question paper, that is fine. But these values you have to remember. Okay, that's it from nuclei chapter. Atoms. So remember, 2 long answer questions. Easily we can derive, if you know the 3 postulates of Bohr atom model. So that is the point where you have to concentrate. Make sure like Bohr atom model is perfectly fine. All the 3 postulates, they are mathematical expression. Everything will follow. If you know all those 3 postulates, easily you can derive other equations. Okay? Right. Exactly. Now, moving on to the next 1 or 2 questions. If the ground state energy of hydrogen atom is 13.6 electron volt, the energy required to ionize hydrogen atom from the second excited state. What do you mean by ionizing an atom? Removing an electron, right? Removing an electron from that atom. Atom, when it is in the ground state, we know what will be the energy of ground state of hydrogen atom, minus 13.6 electron volt. That much energy, that electron possesses that much energy, minus 13.6 electron volt. Okay, if you want to release this electron, if you want to take this electron out, its energy should be 0. It should not be connected with the nucleus. There should not be any attraction between them. So electron should be completely free from the surface. So for that, what should we do? We have to add plus 13.6 electron volt. So how can you ionize electron from the ground state? By adding plus 13.6, so that its energy becomes 0. If electron in the first excited, suppose first excited, we know it has minus 3.4. I told you to remember the value, minus 3.4 electron volt. How can you ionize that electron, that particular case? You have to add how much energy? Just positive of the same amount, so that energy becomes 0, ionized. So in this way, from any orbit, supply that much positive energy, energy becomes 0, electron will be free. And in this case, you are asked from second excited. What do you mean by second excited? Second excited is n is equal to 3, we know, right? Ground state, n is equal to 2 is the first excited, n is equal to 3 is the second excited, and so on. So n is equal to 3, tell me the value. First, second, third, minus 3.4, and the last one is minus 1.51 electron volt, right? Yes. So if you want to ionize this atom, you have to supply plus 1.51 electron volt. So option A. See, advantage of remembering the value. Yeah, many of you already identified. Option A is the correct answer. Okay. Then next one. Hydrogen atom are excited from ground state to of the principal quantum number 4. Yes, n is equal to 4. Then the number of spectral lines observed will be a similar question we discussed before in another live. You remember, number of emissions. If electron is excited from n is equal to 1 to any other excited energy levels. To any other excited energy levels. If an electron is excited to the outermost energy level like this, it can have different transitions. See, it can have like from this to this, right? From there to next one, from there to next, there to next, finally to the initial orbit. Or it can come to this one, then to the next. Or like, these kind of so many like combinations are possible. And we had an equation for that. Yes, yeah. N is equal to, number of transitions, right? Number of transitions. Thank you for those who are responding to this. Like most of you are giving me the correct answer. Number of transitions possible is equal to n into n minus 1 divided by 2, where n is the present energy level. From where is it coming? Question says it is excited to 4th orbit, right? N is equal to 4. Then it is coming back from 4. What is the result? 4 into n minus 1 is 3 divided by 2. 6 transitions are possible. Okay? Right. And look at this. Figure shows energy level diagram of hydrogen atom, right? Specifically for hydrogen atom. Find out the transition which result in the emission of a photon of wavelength 496 nanometer. You are asked to identify in which transition this much wavelength radiation be emitted. Emissions are given there. Here, if you remember the values, it will be quite easy for you. 13.6 electron volt, right? Minus 3.4, minus 1.51, minus 0.85. Yes, we know the values. Hydrogen atom is given in the question. Okay. You have to find a transition in which 496 nanometer is emitted. Okay? Right. So then, let's see what happens. When 496 nanometer wavelength is emitted, what can be the corresponding energy of the radiation? How will you find energy of the radiation if you know lambda? We need in electron volt, right? Because all these energies are in electron volt. So we use E is equal to hc by lambda, right? So 12400 divided by 4960, because it should be in angstrom. This much nanometer will be 4960 angstrom, right? Okay, see, you can cancel these two. We get 1240 divided by 496. If you approximate that 496 into 500, doesn't make much difference. You will easily simplify that divided by 500. See, 124 divided by 50. Right, 124 divided by 50 is going to be 2.48, right? Double of that, 2.48 electron volt. So this much energy is released. 2.48 electron volt energy is released. Now identify the transition from where to where. You are given 4 to 3, 4 to 2, 4 to 1, then 3 to 2, 3 to 1, and 2 to 1. All possible transitions are given. So tell me in which of them. Okay, we don't have names, right, for this transition. Let me number them like 1, 2, 3, 4, 5, and 6. 6 transitions are given. Yeah, 3 to, is it 3 to 2? 2.48. Yes, transition 2 is within. Yeah, S5. Correct only. Transition 2. We can just subtract these two. You will get the correct answer. Approximately 2.5. Correct? Yes. So transition 2. So you have to say n is equal to 4 to n is equal to 2. This transition gives that wavelength of 496 nanometer. Easy. Second question was, which transition corresponds to the emission of radiation of maximum wavelength? Justify your answer. Maximum wavelength gives you minimum frequency, minimum energy. In which of the transitions minimum energy is released? Which of the transition? Minimum energy. The nearest transition. Yes. Transition 1. Exactly. Yes. Izzuddin. Okay. Dhruvil. Yeah. Many of you identified the transition. This is the minimum energy transition, right? because 0.5 1.51 minus 0.85, that will be the least energy released in all these transitions. Okay, so energy transitions done. Nuclei, we'll do as much as we can. At least in this part also we have some repeating questions, especially I'll tell you which are the topics you have to concentrate for long answer questions and numericals especially. The first part is profile of nucleus. Profile of nucleus in the sense we are going to find out mass of the nucleus, we are going to find size of the nucleus, and we are going to find density of the nucleus also. Yes, these three parameters we will calculate right in the beginning to make a profile of the nucleus. Okay, mass, defect and binding energy. Yes, numerical questions. Okay, numerical questions. Long answer, we expected 4 marks from atoms, 4 marks from nuclei also. Atoms, nuclei together 8. It may not be strictly 4 and 4, maybe 5 and 3, depends. Okay, but this chapter has a potential to get 3 mark question, long answer question. Not 5 marks anyway, maybe, right? But 3 marks can be expected. For that 3 marks, you have to just make sure binding energy per nucleon graph, potential energy per nucleon graph, right? Their expression, those graphs and their the conclusions or the observation you can make from those graphs. These questions are repeatedly coming. Okay, you will be asked to draw binding energy per nucleon graph and make some observations and explain your observations from the graph. Similarly, potential energy of nucleon versus internucleon distance graph. Draw the graph, explain, or observation. You have to write your observations from the graph. Those 2 can be the long answer questions. Okay. Apart from that, we don't have any long derivations or nothing from the chapter. The major part of the chapter was deleted, radioactivity. We don't have that part. So it is a very small chapter. Okay, we don't have to lose even 1 mark from that. Easy concepts, make it perfect. So when we come to the profile of the nucleus, we know from the nuclear profile, we first found out the size of the nucleus, right? Size of nucleus, this part, obtain relation for radius. What is the expression for radius? Sometimes we get 2 marks questions. Directly, this is asked before, directly obtain expression for radius of the nucleus. And we know how to derive that, right? Size of the nucleus is proportional to mass number. Mass number is total number of neutrons and protons inside the nucleus. So if you go for the bigger nucleus, size of the nucleus should be of course bigger, more protons and neutrons should be accommodated. So definitely size of the nucleus is proportional to mass number. These size we measured as the volume of the nucleus. Volume should be proportional to mass number, and volume, assuming nucleus as a perfect sphere of radius r, volume will be 4/3 pi r cube proportional to A. 4/3 pi is a constant. I'll say r cube is proportional to A, or r is proportional to A raised to 1/3. R is equal to proportionality constant R0 A raised to 1/3. This R0 was 1.2 into 10 raised to minus 15 meters, right? 1.2 Fermi FM. Yes, this derivation, 2 marks, very easy. Okay, so R is proportional to, right, A raised to 1/3, or finally R is equal to R0 A raised to 1/3. Derivation and also numerical questions we get, okay, to take the ratio of radii, provided that mass number will be given. Simple questions will be coming from like that. So that equation is important. From the profile of the nucleus, size of the nucleus part is important. Now, mass of the nucleus. In the mass of the nucleus part, I'm just running through this, there we defined what is 1 atomic mass unit. We don't have any numerical questions or derivation part or something from this part, but you have to understand what is 1 atomic mass unit properly to proceed. In all other further discussions, we use this 1 atomic mass unit frequently. 1 atomic mass unit is average mass of 1 nucleon, right? That is how we concluded. Actually, it is defined as mass of carbon isotope, nucleus of carbon 12 isotope divided by 12. In carbon 12 isotope, there will be 12 nucleons. 6 of them may be protons, 6 of them may be neutrons. Correct? Yes. Total mass divided by 12 will give you mass of one nucleon. But it is average mass because proton and neutron are not of same mass. Slightly different. Neutron is bit heavier. We know. So one atomic mass unit is actually 1.66 into 10 raised to minus 27 kilogram. 27 kilogram. That is one atomic mass unit. So mass of atom is, nucleus is negligibly small. Size is already negligibly small. We found it is in the order of 10 raised to minus 15, right? 10 raised to minus 15. Mass of that nucleus is in the order of 10 raised to minus 27. Very light. But density part, the last topic from that profiling, density of nucleus. This is also a derivation. There is a derivation for this. Density of the nucleus. Sometimes you will be asked to show that density of nucleus is independent of mass number, right? Independent of mass number. Yes, we know how to prove this. We have radius of nucleus R0 a raised to 1 by 3. This we already derived before. We can say density is going to be mass divided by volume. What is mass? Mass is total mass of the nucleons. How many nucleons will be there in a nucleus? Mass number A, right? Mass number A gives you number of nucleons. Each nucleon has one atomic mass unit, mass. So total mass of the nucleus will be number of nucleons into one atomic mass unit. Volume will be 4 by 3 pi r cube. What is r? R0 a raised to 1 by 3 cube, right? That is what we did. Not square, cube. If you take the cube root of a, the whole cube, it becomes a, right? And that a and this a will be cancelled. A into 1 atomic mass unit divided by 4 by 3 pi into r0 cube a, right? A gets cancelled. A is gone from the equation. Density is independent of mass number. This is how we proved it. Okay, just learn this properly. Okay, that is from the density part. Nuclear profiling is done. Then comes mass defect, the next important concept. Mass defect and binding energy. These two concepts are very important for numerical questions. Mass defect, we know it is like when we consider helium nucleus, we know in helium nucleus atomic number is 2, mass number 4. We expect 2 protons and 2 neutrons inside the nucleus of helium. So if you want to find total mass of the nucleus of helium atom, it should be 2 times mass of proton and 2 times mass of neutron. That is the total mass of the helium nucleus. And we know mass of helium nucleus will be always less than sum of its constituent particle masses, mass of the constituent particles. Some mass will be always missing. This much mass is expected, but we have only a mass less than that. That missing mass is called mass defect. Mass defect. And in this case, mass defect delta M can be calculated as mass of 2 times mass of proton plus 2 times mass of neutron, because there are 2 protons and 2 neutrons. That is expected mass. From that we subtracted actual mass of helium. That is the missing mass. And this is what we do in all the cases. Delta M, okay? Missing mass, mass defect. See, constituent particles, its mass will be greater than actual mass. So sum of the particles mass, right, minus actual mass will give you delta M. And why this delta M? What is the importance of mass defect? This mass defect leads us into binding energy. And what is binding energy? Binding energy is the energy required to bind the nucleons together in a nucleus. Why we need some energy to bind them together? Inside a nucleus, there are so many protons and even neutrons. And neutrons are okay. We are okay with neutrons because they don't have charge. But protons are not like that. They are charged particles, right? Positive charges are accommodated in a very small region. We already discussed that in the beginning of atoms. The nucleus of an atom is negligibly small. Within that space, we are going to accommodate so many protons together. There will be strong repulsive force. There will be strong repulsive force between these nucleons, right? Especially protons. That force is electromagnetic force or electrostatic force. Positive charge and positive charge repel each other. They're supposed to go out of the nucleus because of that. But the nucleus bind them together using some energy. That energy is called binding energy. This binding energy is actually derived from, that is coming from that missing mass. Missing mass is converted to energy. De Broglie hypothesis, he used the same equation, right? A particle is converted into mass converted to energy. Mass energy equivalence, same concept. The missing mass is now converted to energy. That energy is called binding energy. That binding energy is utilized to bind these nucleons together. Therefore, stability of a nucleus is closely related to the binding energy. If a nucleus has enough binding energy, that nucleus will be stable. If it doesn't have much binding energy, then this nucleus will not be stable, because these particles, that nucleus cannot control all these nucleons together. Some of them started going out. They will leave the nucleus. So that is 8 MeV line is the reference line. So you draw this line. No need to draw all these things. Just axis X and Y, then draw the 8 MeV line. That orange line represents 8 MeV. That is a reference line for us. And binding energy should be changing, it is increasing. Actually, binding energy per nucleon graph represents binding energy of nucleons changing with mass number. When mass number increases, what about the binding energy per nucleon? Okay, what do you mean by binding energy per nucleon? Before that, we know what is binding energy of one nucleus divided by mass number, right? This is called binding energy per nucleon. We are not going to take binding energy along y-axis. It is binding energy per nucleon along y-axis. Okay, I hope you remember that. And the graph should touch 8 MeV line somewhere close to 30 at mass number 30, and up to around mass number 170. See, 170. It should be above 8 MeV, but not much higher, close to that 8 MeV line. It comes down below 8 MeV after 170, right? It goes above 8 MeV after 30. Yes. So below 30, above 170. That range you have to remember, okay? A less than 30, A greater than 170. Just remember these two numbers. A greater than 30, less than 170. That they will have binding energy per nucleon less than 8 MeV. Therefore, they are less stable. Stability is less. So not only light elements, those mass number less than 30, even heavy elements, mass number greater than 170, also unstable. Okay, right. So this is the way how you have to explain the graph, right? Binding energy per nucleon is not varying uniformly with respect to mass number. No, it increases first, reaches a maximum value. And what is the maximum value? Maximum value of binding energy per nucleon is 8.8 MeV, and that is for iron 56, Fe56. Okay, that is element which has greatest binding energy per nucleon. And most of the elements, from 30 to 170, most of the elements are having binding energy, average binding energy of 8 MeV. Okay, 8 MeV. So they are stable. But above 170, less than MeV. Below 30, less than MeV. Right, less than 8 MeV. So these are all the things you have to mention in the observations. Okay, right. A is the mass number. Yes, that's what I told you. Yeah. Okay. So this graph, I'm just repeating the same. Okay. Make sure you're okay with this graph. Try once, draw properly. Try to remember the points you have to write down as an observation. Okay. Followed by this nuclear force. See, nuclear force, you have to remember one or two points from this also. Binding energy helps the nucleons, nucleus to bind the nucleons together. For that, some force is required, right? That force is called nuclear force. We have two protons. Okay, we have two protons. These two protons, like inside the nucleus, suppose there will be a repulsive force. That repulsive force is electromagnetic force, right? Electromagnetic force. But binding energy, because of the binding energy, there will be an attractive force acting between them. That is called nuclear force. Nuclear force. So that nuclear force actually hold these nucleons. You know, it hold the nucleons together. Even if there is a repulsive, not be it is weaker than electromagnetic force. That is why they repel and move away from each other. So if it is an unstable nucleus, nuclear force will be weaker than electromagnetic force. At that time it is called weak nuclear force. Okay, it is called weak nuclear force, right? Okay, so the weak nuclear force and strong nuclear force, they have same properties. Nuclear force, two types of nuclear forces, they have same properties except their strength. How can you identify strong nuclear force? That will be stronger than electromagnetic force. What is weak nuclear force? Weaker than electromagnetic force. Exactly. Okay, right. So strong nuclear force will be in stable nucleus. Yes. Then this is the next graph I told you. Potential energy versus like distance graph, internucleon distance graph. This graph also we explained in one of the lives before. So that I told you to remember this graph and its values where we have to make it 0 and all. Actually, what are we trying to do in this graph? We have two nucleons, maybe proton and proton, or neutron and neutron, or proton, whatever may be the combination, same nuclear force will be operating between them. They are charge independent, right? Yes, fine. And if you have two protons or two neutrons or proton, neutron, whatever it may be, if you change the distance between the nucleons, what happened to the potential energy of the nucleons? It is varying, as you can see in the graph, right? This is the zero potential energy. This is potential energy positive. This part potential energy negative. Yes. So when you increase the R, this is internucleon distance R. This distance R, okay? That distance R. If you increase the distance, potential energy first, it was positive. So this is the potential energy graph. It reaches 0 here, turns negative, then reduces to 0 here. See? So potential energy is 0. See, this is the potential energy 0 mark at a distance 0.8 FM. Correct? This is given 1 FM. This point is 1 FM. This is 2 FM, 3 FM. See? And this point is less than 1 FM. It is actually 0.8 FM. Okay? That R0 is equal to 0.8 FM. This point is called R0. So at R0, if the distance is R0, potential energy is equal to 0. Potential energy 0 means no net force acting, no force acting between the two. If the distance is decreasing below R0, if it is reducing below R0, potential energy, if R is less than R0, potential energy is found to be positive. Do you remember what is the meaning of potential energy is positive? What will be the nature of the force? Nature of the force is going to be repulsive. Okay, and the other range, like R is in between R0 less than R less than 3 FM, correct? That is from R0 up to 3 FM, this range. Here throughout potential energy is negative, force is attractive. If potential energy is negative, force will be attractive. If potential energy positive, force will be repulsive. This we explained before. Okay. This graph is also important. You can see this is frequently coming in our paper. When you go to the past papers, you can see this also coming like that. Okay. So try to remember the points you have to mark in the graph and your conclusions, the observations you make. That is what I told you, Dhruvil, you may be asking about this graph, right? These sharps, you don't have to show none of them, like, you know, you can even skip all of them, it's fine. When you ask you to draw, it's okay. That's it from nuclei part. The last part of that was nuclear reactions. Yes, nuclear reactions, like it can be fission or fusion. Remember one equation for both, okay? One equation, one reaction for fusion and fission. We have equations in our textbook. Just remember those two examples. Yes. And numerical question also can be coming from this part also. This energy released in this part. Okay, energy release. Whenever you are asked to find Q value of a relation or energy released in a function, in a relation, in a reaction, just go for binding energy final minus binding energy initial. Binding energy final minus binding energy initial will be the energy released during the process. Okay, that is how we calculate it. Just like we are finding the mass defect and binding energy, in the same way we find energy released during the reaction also. These are the two topics from which we get repeatedly numerical questions. Calculation of binding energy per nucleon and also a calculation of energy released during a reaction. Okay, that is the end of this chapter. Fine, we have one or two questions. Then we'll be winding up in 5 minutes, okay? I'll just run through that semiconductor electronics topic also, like which are the topics you have to just concentrate, that's it. Then electromagnetic waves also. Okay, just 5 more minutes. I'm not going to any questions or nothing, just the topics you have to remember, or for long answer questions and all, I'll just mention them. Okay. Energy band theory for semiconductor electronics. It's a small chapter, we don't have any derivation from that, no equations basically, so this is fully theory, right? We know, that is why some of you like the chapter, some of you not, because we don't have any numerical questions, no equations, but we get theory questions, 3-mark questions repeatedly from this chapter. The problem with that questions, you have to write a lot. If it is a derivation or if it's a numerical question, we have some specific steps, specific thing to mention. But for these long answer questions, we have to write the whole process, especially formation of N-type, formation of P-type, formation of P-N junction. These 3 formations. When you go to through the past papers, you can see they are repeatedly coming from this part. Okay, 3 marks. 3-mark question, formation of P-N-type alone, formation of P-type alone, formation of P-N junction alone, 3 marks questions. Okay, fine, that is one of the long answer questions, formation questions. Then another 3-mark question is like characteristics, P-N junction, forward and reverse characteristics. Okay, and application, rectifiers, the most repeating question from this chapter. Half-wave rectifier and full-wave rectifier. For long answer questions, only these parts you have to just make sure. Okay, fine. Formation of N-type, formation of P-type in extrinsic semiconductor, and P-N junction formation, P-N junction, all the 3 topics below that possible for long answers, characteristics and also application. Application we have only half-wave and full-wave rectifiers, that's it, right, from semiconductors. And when we come to electromagnetic waves, see, we had some conceptual questions from this part, okay, that if we get time we'll do some other time, okay, questions from this. And electromagnetic waves also is very small chapter, we expected 2 marks only from that chapter. The only point I wanted to remind you from electromagnetic wave is you have given a if you go to the topic division, displacement current, just fundamental concepts of displacement current we need, no derivation, nothing, how to represent that mathematically is enough. EM waves, its production, properties, graphical representation. This graph, see, many times you can see it is asked to draw this diagram, okay, graphical representation of electromagnetic waves. So make sure this is fine, okay, how to draw electric and magnetic waves. Electric and magnetic fields are mutually perpendicular to each other, we know. They have same wavelength, right, same phase. If one is maximum, the other one is also will be maximum. So that it's a 3-dimensional view actually, so difficult to draw, but try, practice, okay, just learn how to represent an electromagnetic wave graphically. Yes, that is one point I wanted to remind you. Then the second thing, the mathematical expressions, right, electric field Ex or Ey can be represented as E0 sine kx minus omega t, and the same wave will have a magnetic field Bz is equal to B0 sine kx minus omega t. These mathematical representations are important, we get numerical questions based on that. Okay, we know direction of propagation, that is x, Direction of vibration of electric field, direction of vibration of magnetic field should be mutually perpendicular. All those concepts I hope you remember. So these equation related numerical questions are expected. Okay. Then, and the most important, this is what I told you. These two tables, at least these two columns, you should know this relation. You know what is a wavelength range of electromagnetic spectrum, because you may get a question to write application of electromagnetic wave which has a wavelength 5 centimeter. That is how they ask the question. Wavelength is 5 centimeter. You have to identify the wave. Otherwise, if you know the wave, we can write something. We know so many applications of all these waves. We already learned. But they won't ask what is the application of microwaves. They ask what is the application of 5 centimeter wavelength. 5 centimeter wavelength comes to this region. It is microwave. But for that, you have to identify it as a microwave. Then only you can write the application. Okay. So learn this properly. Okay. These two columns. When you go through the past paper again, you can see questions are repeatedly coming in this way. They won't mention the wave. They will give you the details. Wavelength mostly. So from the wavelength, you can identify and you can write the application. Okay. Yes, that's it from electromagnetic waves. And we had 1 or 2 questions from that. That's okay. So make sure all the long answer questions that we mentioned, you know, this part is not we don't have much long answer questions there, because each chapter has a weightage of 3 to 4. Correct? So 5 mark questions are not expected from there, but 3 mark questions can be asked. I mentioned all the topics which you have to concentrate for those long answer questions. Okay, we are already running out of time. So we are winding up now. If you have any questions. Yeah. Was it lagging? Okay then guys. Thank you all and good night.
Brilliant Qatar, your trusted coaching partner for IIT, JEE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.